Okay, thanks. So because this talk was not recorded at, I think, Web3 or DevCon, I'm also going to use this. So we're recording it now, and we'll post it online. So for those of you who have attended either of the or both of the previous talks, I apologize. You're going to hear me repeating stuff again. So hi, I'm Eli Ben Sasson. I'm the chief scientist of StarkWare. We co-founded the company about 9 months ago. Just announced 2 days ago a 30 million A round. Previously, we had a 6 million seed round around January. We're 15 developers, all focusing on using Starks, which I'll talk about, in order to improve mostly scalability in blockchain applications, but also with applications to privacy. And so what I'll talk about today is, first of all, what do we mean when we say a Stark? Then we'll compare Stark to other of the many technologies out there. There are 3 that we will compare with because they are the ones that are currently either deployed or soon to be deployed within blockchains. Those are Snarks, recursive Snarks, and BulletProofs. We'll focus mostly on the applications of Starks for scalability, which is what interests StarkWare most. And that's the core benefit of a Stark, is for scalability, though it also can deliver privacy in the form of zero knowledge. And then we'll discuss potential use cases. So there's a lot of discussion of ZKP and zero knowledge proofs and what they can deliver, but we would like to refocus the attention to the property of computational integrity. And integrity is defined as the quality of being honest, being true and correct. So computational integrity, by logical deduction, is the quality of a computation being performed honestly or correctly. And what this means is that when someone reports to you the output of a computer program on specific inputs, you would like to be able to know that the output is correct. Now, a simple example of a proof of computational integrity that everyone can probably recognize is that of a grocery receipt. It achieves the purpose of establishing and enforcing computational integrity. Here, the computation is that of summing up a bunch of items and concluding that the total sum is the number at the bottom that you should pay. And this string of characters is a proof of computational integrity because both the buyer and the seller can look at it, can check it, can argue about its correctness, and reach the same conclusion, whether it is right or wrong. So classical proofs of computational integrity, such as audit reports and grocery receipts and restaurant bills, have a lot of good things about them. They've been around for a long time, and we know how they work. They're also deterministic, meaning that any 2 executions of the computation or of checking this thing will always result in the same result. There's no probability of error in deciding whether this is a correct or incorrect proof. And they are also one-shot. This piece of paper, you can walk with it and show it to anyone. They will reach the same conclusion. Now, modern proofs of computational integrity, like Starks and zero-knowledge proofs and things like that, all of them have several things that are different from this situation. First of all, they use randomness. They are not fully deterministic. They do have a small probability of error that you usually cap at whatever you decide to be a manageable error, 2 to the minus 80, 2 to the minus 128, something like that, 128 bits of security. And they also involve some form, at least initially, of interaction, which means that in this example, the grocer and the buyer would do a little bit of back and forth in their in generating a transcript of something that would end up being the receipt. Okay? You can then, in many cases, under certain assumptions, remove this interaction and go back to this world. But when they are studied and defined, it's best to view them as an interactive process. So compared to the good old proofs, we seem to have lost a lot. We use randomness. We allow errors. We allow interaction. It's much worse than this situation. But we also gain a lot, and that's the point. So these modern kinds of proofs, originally called interactive proofs, were invented famously by Shafi Goldwasser, Silvio Micali, who's now also famous as the founder of Algorand, and Charlie Rakoff in 1985. Famously, Shafi Goldwasser and Silvio Micali, both professors at MIT, received the Turing Award 2012 for their invention of interactive and zero-knowledge proofs. And what you get for the price of allowing randomness and error and interaction is, perhaps now most famously within blockchain world, is the aspect of zero-knowledge or privacy preservation, which you could analogize by thinking that you can sort of blank out some of the inputs in this grocery receipt and still be as assured that this is the correct sum. Okay, that's a decent analogy without going into more details. The thing that we would like to focus more on is, which is another attribute that you can obtain with these kinds of proofs, is that of scalability. And when I say scalability, I mean the following, that if you apply these techniques, these proof techniques, to a computation that takes t cycles, and think of t as going to infinity, some parameter that grows, then when you measure the time needed to generate a proof, you can generate it in nearly t cycles, more formally quasi-linear, or something that looks like t times a small polynomial in the logarithm of t. But it's nearly t cycles, and you can verify it exponentially faster than it would take you to do the naive verification by recomputation. And that means some polynomial in log of t cycles. So a system, so these proof systems, these systems for generating these grocery receipts or beefed up grocery receipts could be designed with this property of scalability, in addition to zero-knowledge. And the last one that is very important in the context of blockchains and smart contracts, but also in other settings, is that of universality, which means that you can apply it to any computation. And that means that you can get these grocery receipts not just for summing up the items in a store, but for doing much more complicated computations. And some examples of things one could apply these proofs to are, first of all, you could prove that you paid all your taxes on your cryptocurrency transactions for the year 2017. You could do it in such a way that verifying this will take much less time than going over this report with all its transactions. You can prove that you control at least 10 ethers as of today. You can do so without exposing those ethers or their addresses by use of zero-knowledge. A crypto exchange can prove that it is in the black and show it to each one of its customers with an individualized proof that says, that refers to some Merkle commitment of all of the exchange positions and balances, and proves to that individual customer your account has been taken into the computation, and do so in zero-knowledge. This is something that we wrote a short piece about, and it appears on the Coin Center blog post. So there are many systems that have some of the attributes of zero-knowledge, scalability, universality. I want to explain what we mean when we say Zk-Stark. So proof systems like zero-knowledge proofs and interactive proofs and their variants, and there are numerous variants of them, have been studied extensively in theoretical computer science and in cryptography for 30 years, since 1985 or so. And there are many, many beautiful and deep and important constructions of them. Okay? And more recently, over the past 5 years or so, there have been starting to be a lot of code bases that implement various of these systems. And this list is growing all the time. A very good reference point is zkp.science. There's a long list of papers and surveys and results and links to various proof systems. That's a good resource to read more about this. And I won't go into describing the different attributes of all of this theory and all of these different implementations. I just want to focus on what we mean when we say a Zk-Stark. So a proof system of computational integrity, we'll call it a Zk-Stark if, when you open up its acronyms, you have the attributes of a Zk-Stark. So Zk is easy. It means that you can get zero-knowledge. Private inputs are shielded. Scalable is what we discussed earlier. It means that The proving time scales almost linearly in the in the time it takes to naively compute the base computation. And at the same time, simultaneously, verification is exponentially faster than t. That's the second attribute. Transparency means that all messages generated by the verifier or on behalf of the verifier, or if you imagine this circle of trust that the verifier says, this is what I need to rely on in order to assume that the proof is correct. Everything that goes within that circle of trust, that amount of computation, everything that goes out of that circle of trust is only public random coins, which means that you can now easily convert this system into, for instance, one where that randomness is coming from a blockchain, from like block headers or things like that, or you apply what's called the Fiat-Shamir heuristic, and you remove the interaction by assuming that there exists some function that's hard to guess its output given an input. The last thing that a system must satisfy in order to be a zk-Stark is that of an argument of knowledge, which means that if you see a proof, then you know that there would have been some way to extract the actual witness that is hidden under the proof by sort of rewinding and interacting more with that prover. So what you see is a very short transcript of the interaction between a verifier and a proof. You see a very short proof, but knowing that the proof succeeds with, let's say, 99% probability, this sort of interaction across different randomness immediately implies that the prover knows a witness for the statement. So it's not the same to say, I know that a statement is true. That's not the same thing as saying, I know the witness that causes this statement to be true, right? Any transaction on Bitcoin or Ethereum, I know that there is some key that is sufficient to transfer control of those funds. But that doesn't allow me to transfer control of the funds. It's very important that my transaction prove that I know that key when I transfer funds. So you need this property. And a system that has all of these properties would be called a zk-Stark. So an important comment is that zk-Starks may be interactive. They don't need to be so, but they could be interactive. And because of the transparency, it's easy to go from an interactive version to a non-interactive in several different forms. You could use the blockchain as a source of randomness. This could actually save a lot. You could work with a considerably smaller security parameter and much shorter proofs and still feel that this is sufficiently safe. Or you could apply what's called the Fiat-Shamir heuristic and make it non-interactive. And there are already out there several implementations of open source, MIT license code bases that are Starks. So the first Stark is the Psi POC. You can find it on GitHub. The second one is libstark, that is actually a zk-Stark. And StarkWare is writing from scratch its new code base that is more, so these are academic versions, good for getting estimates of costs and how things work, but I wouldn't use them in any system that carries significant value because there should be some, bugs and things that don't work quite well there. And StarkWare is writing its own code base that soon will show you some numbers of our most recent implementations. Now I want to compare Stark to Snarks, recursive Snarks, and BulletProofs, especially in light of this question of scalability, which is the main thing that Starks are really good at. So again, Starks also can deliver privacy and zero knowledge, but scalability is where they really excel, and that's where StarkWare wants to put them to use. So what do we mean by scalability? And this is sort of an abstract discussion. So first of all, let's consider the case of a naive verification, as you would do with a grocery receipt. So as this computation time grows, and you can think of this as processing many transactions on Ethereum or breeding many generations of CryptoKitties. So as you increase the running time of the naive computation, if you would check the computation the same way you check a Bitcoin's blockchain or the same way that you check a grocery receipt, you would be rerunning the same computation. So the proof activity time, both generating the proof and verifying the proof, would scale exactly linearly with the size of the naive computation. That's why it's naive. There's nothing deep or interesting about this. So A Stark, by definition, should look like this. The proving time should be, hopefully as close as possible to the black line, but it will never be below the black line. That's mathematically impossible. You can't prove something faster than it takes to do the naive computation. If you could, you're using the wrong computation in the naive case and just move to a better computation. So assuming you have the best computation you could think of, the blue line is never going to be below the black line. And I don't believe that, in my lifetime, we'll see the blue line actually, touching the black line and going linearly with it. That relates to some fundamental open problems in theoretical computer science. For instance, to do this, you'd probably need to have linear time, FFTs, which we don't know how to do, and other things that, again, not in my lifetime. So the blue line is always going to sort of go a little bit higher, and as you grow up in T, it's going to diverge more and more from the black line. That's what a quasi-linear function looks like. But again, I don't believe it's possible to really reduce it to closer. And the more important thing is what happens to verification time. So within this circle of trust of the verifier, all of the computation needed to be done should scale logarithmically with T. And that's what the logarithm function looks like. So as I said, I want to compare Starks to other popular technologies. Zk Snarks, they're used famously in Zcash. Proper disclosure, so both I and my co-founder and co-chief scientist in the West, Alessandro Chiesa, were both co-authors of the Zero-Cash paper and founding scientists of the Zcash cryptocurrency. We supported strongly and admire Zuko and his team for the great progress that they've made now with releasing Sapling. But as a scalability technology, Snarks are not quite as good as Starks. And the reason is that you do see that the prover time scales pretty nicely with the naive computation time. And you do see that verification is scalable. But within the circle of trust of the verifier, there's this trusted setup that grows superlinearly with the size of the computation. Okay? So it's both a trusted setup, and you all probably know about the trusted setup, and that it's a problem to deal with it and do it correctly, and it's a single point of failure, and you would like to find ways to remove it. Luckily, there are Starks that do remove it. But it also grows superlinearly with the compute time. So it means that even if you're willing to trust the trusted setup and you want to apply Snarks for greater and greater computation size, you would need to generate and transfer these keys to of greater and greater length and generate longer and longer ones. Okay. The second technology that I want to mention, recursive Snarks, that is going to be deployed by Coda for scalability solutions, has a trusted setup, but it's a very short one. So in that sense, maybe it's not so bad. I mean, it's still a trusted setup, but short. It doesn't grow linearly with the computation size. The thing is that when you do a recursive Snark, the proving time, although it follows this, it follows it at quite a large distance compared with a Stark or even with a Snark. So the blue line goes up a lot. Now, theoretically and abstractly, you could say, well, this doesn't really matter much. It still is scalable in this sense that the proving time goes pretty much like the black line. But it does matter concretely because, for instance, whatever is the delay that you're willing to tolerate for generating a proof, what will happen is that, let's say it's one block delay, that you need to generate, let's say, a recursive Snark or a Stark within one block. It means that within that one block, the amount of computation that you can cover is small, and certainly smaller than you could do with a Stark and also with a Snark. And if it's too large, it could even be below the point where you gain any benefit for scalability. So the farther up this line you are, it means that the difference between naive verifying time and verifying time is larger. But if you have the block delay limit or some other delay, like 1 day of computation on a AWS cluster, you'll pack in less computation, and you'll get less of a punch of scalability from using something that has a very large proving time. And finally, Bulletproof, now deployed on Monero, is another technology that is used for privacy. It has zero knowledge. The main good thing about it is that the proof length, so it's a zero knowledge technology. The main thing about it is that the proof length grows scalably with computation size. But both proving and verification time grow superlinearly with T. So even though the payload is very small, the verifier must run a computation that is larger than naive computation. So as a scalability solution, Bulletproof saves you nothing in terms of computation time for the verifier, right? It saves you only in communication complexity, but it makes things worse for both proving and verifying. So here are some measurements that compare the actual verifying time of Bulletproof, first from the Bulletproof paper of Dan Bonnet, Benedict Bunz, and others. And there is a more recent Rust implementation on Dalek cryptography that what I did with this one is I just downloaded on this computer, this laptop, T440, and I compared it to the Stark verifying time, and compared all of this to naive execution of Pedersen hashes. So Pedersen hashes are very important and used already, for instance, in the Zcash sapling circuit. They're a kind of a hash function that has very nice provable security guarantees. And as you can see here, the verification time of Bulletproofs matches this kind of curve, but a little bit higher up, whereas the verification time of Stark doesn't. And you can see that at some point it goes on and is going to cross it and become cheaper to verify this particular computation than to run it naively. And that could never happen with Bulletproofs, just because by definition, that's the way it works. Okay. So I want to zoom in and show you some numbers for this scalability aspect, as we already have them in the code that our team has written. So these are all numbers that were generated from this particular laptop like a few days ago using the latest code that we have there. So it's all in single thread. This laptop is not the fastest, 1.8 gigahertz running time. And here so you do roughly 5 Pedersen hashes per milliseconds, and then naive computation and proving and verification looks pretty much like this. This is the proving time required, and it basically goes from 1 Pedersen hash up to 8,192. We'll see these numbers later again, but it goes in jumps of 2. So 1, 2, 4, 8, 16, 32, 64, and so on. And this is in milliseconds, both cases. So the main thing you can see is that the verifying time hardly grows. As we go from 1 Pedersen hash, verifying the correctness of 1 Pedersen hash, to verifying 8,000 of them, you only double. So you did 8,000x on the proving time and on the naive computation time, but the verification time went up only by 2x. And currently, the ratio between proving time and naive computation time is roughly 100x. So it's 100x more expensive to produce a proof for a Pedersen hash than to do it. I should stress that this is after only 6 months of engineering work, and we expect all these numbers to go down significantly. I mean, not the black line, but we expect both the blue line and the green line to go down significantly. These are just the numbers we're comfortable displaying now. I want to say a little bit more about the virtues of transparency, no trusted setup, and use only of public random coins. So first of all, you eliminate a single point of failure, which is the trusted setup. And also, the public can find it easier to believe and have trust in the system. Think of a state or a big bank wanting to use a proof system and convincing the public that everything there is done correctly. So you would really want it to say, I have nothing up my sleeves. It also facilitates continuous deployment of minor upgrades to your network. You don't have to batch them into big things because of the need to generate a trusted setup, which is very complicated. As I said, it reduces the trust assumptions. A government or a big bank could come to the public and say, we're using this system, but you really should trust it because there's nothing up our sleeves. There's no part of it that we could have manipulated in this proof system. And the technology that we use to create these Starks happens to be rely on very lean cryptography, basically on the existence of collision-resistant hashes, which is a very kind of old and very trusted cryptographic assumption. It also makes the system post-quantum secure, leads to faster proving and verification time, and all of these systems rely on more old, peer-reviewed, information-theoretic, math-proven techniques than some of the newer stuff. So just a little bit of summary. In terms of trust assumptions, do you need a trusted setup or not? So a Stark doesn't need one, and BulletProofs doesn't need one. They're both transparent, whereas a Snark does need. The crypto assumptions in both Stark and Bulletproof go back a little while. So with Starks, it's collision-resistant hash. With Bulletproofs, it's the hardness of the discrete logarithm problem. But they're both pretty old assumptions. The ZK Snarks rely on knowledge of exponent assumptions, which are a little bit newer and would require a little bit more time to gain acceptance. And finally, quantum safety. So only ZK Stark compared with Snark and Bulletproof has that. Both of these techniques rely on number-theoretic hardness assumptions, which are breakable by quantum methods. So this is a table that we also showed about half a year ago in consensus. And back then we said that a single transaction on a ZK Stark went down from the academic paper where it was half a megabyte, went down to 80 kilobytes. Now, half a year later, we're already comfortable saying that we can do it in 45 kilobytes. So this would be for one kind of transaction, either a Zcash style one or something that transfers value on Ethereum or Bitcoin or something like that. So it should be roughly 45 kilobytes. That's still 200x larger than the 200 bytes of a Snark, and roughly 30x larger, not roughly, exactly 30x larger than in a Bulletproof. So definitely our proof sizes are larger. We do believe that these numbers are going to go down, and we don't know yet of a lower bound. But these are the numbers we're comfortable specifying right now. It's more interesting to look and see what happens when you go to 10,000 transactions. Then, even though you multiplied this by a factor of 10K, proof size only went up by 3K in our setting. And verification time also went up pretty much by 3K. Now, in a ZK Snark, you stay with pretty much the same size proof, 200 bytes, but the trusted setup key went up by a linear factor, as it should. So it went up from 50 megabytes to 10K times 50 megabytes, which is 500 gigabytes. Okay? And with Bulletproofs, the proof went up a little bit, which is really great. But the main thing is that the verification time, whatever it was for this case it's going to be 10K times that verification time. So if it was 1 millisecond here, this would require 10 seconds. Whatever is the verification time here you need to multiply it at least by a 10K factor, maybe by more because things don't grow quite linearly. They grow slightly superlinearly. Now I want to tell you a little bit about how we construct Starks. So I just want to see how much time. Okay. So we start with a general computation that we would like to generate a proof and a verification for, and we need to do something with it. The first thing we do with it is we convert it into something we call an AIR, an algebraic intermediate representation. For those who have already dabbled in Snarks, they're familiar with R1CS constraints. So AIRs are a generalization of R1CS constraints, which means that each R1CS constraint system can be viewed as a special case of an AIR. special case because each constraint there must be the product of two linear forms. With an air, you can do that, but you can also use polynomials of larger degree. You can have constraints that are not just the product of two linear forms. You can do more. And in some cases, that actually gives you more efficiency. Okay. So what is an air? We think of the state of the computation as captured by a sequence of field elements. And we'll see some examples later on. So maybe I'll give this example now. Suppose my computation is something as simple as generating the ith member in the Fibonacci sequence. So the Fibonacci sequence starts with 1 and 1, let's say, and then so the first and second elements in the sequence are 1, 1, and then the third one is the sum of the previous two, which makes it 2. The next one is the sum of the previous two, which is 1 and 2, it's 3. Then you always sum up the last two guys in the sequence to get the next guy. Okay. So suppose your computation is trying to figure out what is the millionth element in the Fibonacci sequence. So what does this computation look like? It's a loop that goes on for 1,000,000 steps. But in each step, all it needs is like 2 registers, one to remember the last 2 elements in the sequence. And then it sums 2 of them. In the next step, it's going to sum both of these registers and put the result in one place. And then it's going to copy the very last one from the previous state and put it somewhere else and repeat this process. So that's pretty much what the program looks like. So if you convert it to an air, your state would require 2 field elements, right? And then if someone presents to you this table that has 1,000,000 rows and 2 columns and asks you, or you ask yourself, is this thing a valid execution trace of the computation of the Fibonacci sequence? So the thing you would need to verify is basically to apply a certain simple polynomial relation on 4 entries of the table each time. So you want to take the first 2 and the next 2 and check 2 things, that this guy equals this guy, and that the sum of these 2 guys equals this guy. So you have 2 equations. One says this minus this equals 0, and the other one says this plus this minus this equals 0, right? And you want the same set of equations to be applied 1,000,000 times to each pair of consecutive states. So an air for us is defined by saying, okay, the state has 2 field elements, and the set of constraints we're checking are these 2 particular constraints. One that is an equality, like a diagonal inequality, and the other takes the sum of 2 elements and checks that it equals this guy. So if you take those 2 constraints and the number 2, which says my state size is 2 and my constraints are these 2 constraints, you have defined an air for the Fibonacci program. Now, the Fibonacci program is a very simple one, right? If you want to do repeated Pedersen hashes and then check something about value transfer in the leaves, your program will have wider states with more field elements, and the relations between the current and the next step are going to be more complicated. There'll be more equations that check stuff, and these equations are not going to be simply to add 2 elements and subtract it from the third. It might be take the product of 5 of them, and subtract it from the product of 3 other guys and check that that thing equals 7, right? But what our team is doing, and will be doing considerably in the future, is taking all kinds of computations and reducing them as efficiently as possible into number of registers that we need and number of equations that we need in order to capture the computation and do so safely and efficiently. Once you did that, there's a whole lot of algebra and cryptography that goes into it. But the nice thing about it is that all of that is the same no matter which air you write. So different programs would differ in the airs they generate, but after that you apply it through the same machinery that uses a lot of FFT-like algorithms and the Fry protocol and Merkle trees and whatnot, but it's generic and applies in the same way to all of them. Now, in the long term, there will be tool chains that take a program or a smart contract written in your favorite language and convert it into an heir, which could then plug into the whole Stark machinery, okay? And do it efficiently. That's going to be there in the long term. Think of it as a compiler to heirs. In the midterm, it's more reasonable that we'll have domain-specific languages that would maybe optimize for some very specific crypto primitives like hashes or signatures, things like that, and allow a little bit of manipulation of other logic, like addition of integers or things that could be used in smart contracts and financial systems. But in the short term, and that's the first thing that at StarkWare we're doing, we're just hand optimizing heirs for very, very particular computations to be deployed safely onto blockchains. And now I want to show you some numbers for the very first internal milestone that we took on ourselves. Again, we incorporated 9 months ago, and we started programming 6 months ago. And one of the first things we said, let's just do a full Stark for proving the following statement. I know a leaf in a Merkle tree of depth D with Merkle root R, where D and R are parameters. And we're using the Pedersen hash to construct this Merkle tree. Now, the reason we chose this, and those developers among you will recognize this is not just some arbitrary computation. It's one that is very deeply tied to a lot of the very first things that you might want to do with a Stark. And I see Barry agreeing here. It's the main component in the shielded transactions of Zcash, both in the sprout circuit and in the sapling circuit. It is also useful if you want to work with verifiable delay functions based on repeated invocations of hash. A lot of the scalability solutions that will be discussed later on today have to do, or at their core, there will be the process of showing correctness of authentication paths in Merkle trees. So it's a very interesting first milestone. And so we said, let's do it, and I want to show you some numbers for this. So what we have here, on the top we have proving running time as a function of the number of, the depth D, or the number of invocations of the Pedersen hash, and it's on a, basically on a doubly linear scale, right? So, and what you can see is that the proving time goes up in jumps that are roughly at powers of 2. So each time you go, at some point things blow up by a factor of 2. I suspect that maybe this one is a little bit off. It probably should be here, right? Like this is probably 64 here and here. But the verifying time hardly budges with the increase in the number of Merkle paths. And that's because of the scalability aspect. Now, again, I want to emphasize this is after 6 months of work, and we expect the numbers in both of these things to go down significantly. This is on here we have things on a doubly logarithmic scale, measured in seconds. So as you double the number of hashes, you expect the proving time to roughly double and a little bit more. And that's roughly what happens here. So by the time you reach 8,192 hashes, it takes you roughly 4.5 minutes. And here we show verifier time as a function of the number of hashes on a singly logarithmic scale. So here, as you go from number to number, you're doubling the amount of computation, but the running time of the verifier is measured on a linear scale. And that's because verifier time scales very slowly with the size of the computation. So as you go from 1 to 8,000, your verifying time is only roughly doubled. And again, all of these numbers, we expect them to go down. In particular, this is on a single thread. So if you do it on a quad core, this will probably have to divide by 4 or so.
What's the curve like that you're hashing up, that you're using for hashing?
Just one second. It doesn't matter that much, but it's a curve. Its security is 128 bits, which means that it is like 258-bit prime that we're using. Okay.
Are there like certain primes that are like field sizes that are more efficient on the Stark setting like there are in Stark?
The ones that would be more efficient for building a Stark are the ones in which the ambient arithmetic is on a CPU is faster. So you have no concerns. There are no elliptic. I mean, you use here the elliptic curve to get the Pedersen hash, but it's not like you require. The Stark doesn't require anything special about that. It does need the Stark proof does need p-1 to be divisible by a large factor of 2 so that you can do FFTs and also something called Fry efficiently. In that respect, also in Snarks, for similar reasons, because you also need to do FFTs of similar size, similar primes are used, but that's the only constraint that you have. Okay. So you have more freedom in picking the primes that you work with. So this is the size of the proof, again, as a function. And this now goes on a much larger scale. So this is, again, on a singly logarithmic scale. Each time here we multiply by 10. So just to take a number. For 10, this is, I think, 10 billion, right? Because this is 1 billion. So for 10 billion, for a computation that checked a Merkle path or a number of hashes that is 10 billion, the size of the proof in kilobytes would be 122 kilobytes if you're looking at 80 bits of security, or 300 or so kilobytes at the 128-bit security level. And again, we expect these numbers as well to go down, even for this case. But these are the numbers we're comfortable presenting at this point. And then this is an interesting plot. Suppose you ask yourself, suppose you want the verifier to run, say, on Solidity, on the EVM, and check the correctness of a proof. What is this verifier doing? So most of what it's doing, more than 95%, if not 99% of its computation, is checking hashes in Merkle trees. Because the way a Stark proof works is that the proof is composed, first of all, of a sequence of Merkle commitments. And then the randomness comes in, and the prover exposes a bunch of entries in those commitments, and then there's some simple check applied to those exposed entries. And the checks applied to them are rather simple. It's like adding 2 of them up and checking that it equals the third, things like that. So most of the computation of the verifier in verifying a Stark is checking that the authentication paths within these Merkle trees are correct. And if we look at the number of authentication paths, so let's, for 10,000 hashes, if a prover proves to you that she saw 10,000 hashes, her proof would consist of, well, between 1,200 and 2,000 hashes. That's what you would need to verify. So this is already 5 times less than checking those 10,000 hashes yourself. And of course, if you go to some huge number, then the scalability aspect of Starks really kicks in. So instead of checking 10 billion hashes, as a verifier, you only have to check between 4 and 6,000 hashes. Again, you went from 10 billion to 4 to 6,000 hashes. And all these numbers, may go down as we continue developing these things. This is useful both for when you think about gas costs for deploying things on say, Ethereum. They're also useful if you think about things like recursive application of Starks. So you would like a Stark prover to prove that she saw Stark proofs. So most of what she needs to prove is that she checked a bunch of hashes. And the numbers that you would need are dictated by this graph, which, again, will go down. Now, we get asked a lot, what about recursive Starks? When are you doing them, and so on? So our answer to that is there's a lot that can be done already with non-recursive Starks. In fact, in most cases, if you care about scalability, you're much better off using a Stark as opposed to a recursive Stark. That's not necessarily the case with Snarks because of the trusted setup that grows with computation length. With a Stark, because you don't have the trusted setup, as the computation size grows and grows, you're still, in most cases, better off working with a Stark rather than a recursive Stark. Now, if you get to a point where you want to prove that you saw many shielded transactions that have zero knowledge, then also in the Stark world, you may want to batch them using a recursive Stark. And for that, as we improve the constructions and bring down the number of hashes and also the cost of each one of these hashes, of course, the work of the recursive Stark prover is going to go down with that. So we're first going to optimize the number and reduce as much as possible the number of hashes that it takes to verify a Stark. We're also pushing down the computational complexity of each one of these hashes, and that will be my next topic. And after we're confident with those numbers being small enough, it would be much more meaningful to look at how efficient is a recursive Stark. But already these numbers give a lot of room for optimism, combined with the running times that it takes to generate them. So just, consider this. 8,000 on a single thread takes roughly 4.5 minutes, but to verify it only requires like between 1.5 and 2.5 hashes. Okay. So we received basically the first project that we received is this very considerable grant from the Ethereum Foundation that we're very grateful for. And it's a 2-year performance and milestone-based grant, and I just want to report on an update. So the main deliverable that we should reach, according to this grant, is the ability to run a Stark proof at a rate of 100 hashes per second on a quad-core machine. And if you go back to the numbers we showed you, so on this particular laptop, which isn't the fastest of them, on a single core, we're already running at 100 Pedersens for 3 seconds. So we're not very far, 6 months out from the beginning of the project, we're not very far from delivering on the main milestone we were requested for. Another thing we were asked within the grant is to examine and suggest Stark-friendly hash functions. And what we did is we first defined the complexity parameters for anyone wanting to define a Stark-friendly hash function. And we have already started distributing this report, and we will put it online. In particular, tomorrow there's a talk that I highly recommend by Dmitry Khoratovich, a security expert, that will present a proposal of a Stark and Snark-friendly hash based on AES that is very, very efficient. Another thing that I want to tell you about is another potential Stark-friendly hash function that what we did is we partnered with the team of Professor Vincent Reimann, famously known because he is the Rye in the Reindel cipher scheme, which is the basis for the AES standard that everyone uses, one of the most reliable ciphers in use today. And Dr. Tomer Ashur and Simon de Jose designed a very beautiful AES-based construction of a cipher and a hash. They call the cipher Jarvis. This comes from the Tony Stark Iron Man comic series, because Jarvis is the, I guess, the butler or the helper of Tony Stark, and Friday, I think, is another assistant. And the bottom line is that they are roughly 25x Stark friendlier than a Pedersen hash. And what we'll do next is they will post their report. We will first of all circle it among experts to see if it actually holds and sticks and there are no attacks on it. And we will also later on with their team conduct what is usually done in such cases, which are all kinds of competitions for breaking it for several rounds, breaking it for smaller fields, and setting so that the community will be able to gain more confidence in it or break it, and then we move on to the next thing. So I don't want to go into too much detail about the construction. Those interested should go to Dr. Tomer Ashur's blog post and read more about it. The main thing is that they are defined over binary fields. The number of rounds that you apply this transformation has yet to be defined. It's between 6 and 10. The security is Reindel-style analysis, which makes it a little more believable in the sense that there's a lot of work that has been done to similar constructions, and that's very important for security. I do want to mention, because there were some tweets asking about this, so Jarvis, as currently defined, is not prime field friendly, and hence it's not Snark or bulletproof friendly. Okay, so read more about it here. And to support including Stark, Jarvis, and Friday into Ethereum, we're going to need EVM opcodes for binary fields, addition, multiplication, maybe also division, and for hash functions like Friday, but also Blake, which is a really super great hash function and would be good for Ethereum to include. And we will submit an EIP request to support that. Just to show you some numbers, so I don't want to go over all of them. The first two rows are from the Stark paper. If you look at Pedersen, the number or the complexity of it is roughly 2,000 according to this metric. MIMSI is 10 times faster, and Jarvis is going to be 4 to 2 times faster than MIMSI, or between 20 to whatever it is, 2,000 divided by 60 times faster than Pedersen. And the effect you should, so if Jarvis is adopted, it means that these running times should go down by a factor of roughly 25. So instead of 263 seconds, it should be roughly 2 seconds to generate a proof that you saw 8,000 Starks.
12, yeah.
What?
11 or 12.
10.
10? Oh, sorry. Yeah. Okay. I'm not good with numbers, right? So, okay, I meant whatever happens when you take 263 and divide it by 25, which some people say it's more like 10.
It's more like 10.
Okay, maybe. Okay. Now, the numbers here are not going to go down by that much, maybe by sort of 10%. I'm afraid of saying stuff that will. Yeah, so expect these numbers to go down by 25x. Because the proof size will go down, and the verifier running time is correlated linearly with the proof size, but it doesn't go down as dramatically as the proving time.